at p-values, we're now going to move on and consider confidence intervals, which is another measure of precision. So the aim of this presentation is to explain the concept of confidence interval and its relevance to significance, to clinical significance. Now, when you consider articles, you sometimes find these little symbols presented here, these dots with lines running through them, and you might have thought, well, what are these things relating to? Well, they're a graphic representation of your confidence interval, and the longer the distance between the arms, if you like, the greater the confidence interval and the less confidence you can have in the result. So ideally you want everything to be really confident and in a small little ball on your graph. Okay, some of you may recall this slide from the previous presentation on p-values. Now, statistical significance alone cannot convey the complete picture of effectiveness of an intervention. Statistically significant result may not have a meaningful impact in clinical settings, while the use of confidence interval helps researchers to interpret both statistical as well as clinical significance. Confidence interval provides information about the magnitude of the effect and uncertainty surrounding it. P-value of statistical significance alone cannot convey the effectiveness of the intervention. Both statistical significance and clinical significance are both important for interpreting the clinical outcome. So the confidence interval provides a slightly different estimate of statistical truth. It provides a range of the true effect observed in a study. Confidence interval provides a range of possibilities of effect within which the true value would lie. That's between 95 or 90% of the time. So basically, we may have a drug that produces a significant effect. So patients take a drug and it produces a good result, a beneficial result, a significant result that's not down to chance, it is down to the pharmacological action of the drug. But we don't know how effective that drug will be in the population. If it only produces that significant effect in 1 in 100, then it's not really going to be of any strong value therapeutically, because we want it to be applicable to as much of the population as possible. So any treatment, although it may be effective in certain individuals, to be cost effective, to be probably clinically worthwhile, it has to be valid and occur in a number of individuals. So the drug may work in 1 in 1,000, but that's really no use. Even if it is significant, it's no use, the numbers are too big. So what we need to know is we need to know exactly how likely that effect is going to be observed. With what confidence are we going to see that effect in higher numbers? And really we want to see in statistical terms they say the value, but as clinicians we're interested in outcome. So we want to know really how likely are we going to get that result 95% of the time. So if I do treatment A to a patient, will I see that result 95% of the time, or won't I see it? When it does happen, it may be significant, but it's no use to me if I don't see it. I need treatments to be effective 95–90% of the time. I need my implants to osseointegrate 95% of the time. I need my aligners to move teeth 95% of the time in patients. So how reliable is the treatment? And this is where confidence interval comes into play. Now I hope that this slide helps pull some of the various points together for you. So confidence intervals, they provide a range within which the observed effect or value would lie, or range of uncertainty. 95% confidence interval is the most commonly used in hypothesis testing. Now this is 2 standard deviations either side of the observed value or mean. It is the range of values that we can be confident that the true value lies. So we have, if you recall, our standard distribution, and we have our standard deviations, and you may also recall the 68, 95, 99.7% rule. Now, we would like to be fairly confident that our observed value would lie somewhere within 2 standard deviations, or 95% of the time. So I know some of you are interested in digital printers and aligners, so I tried to come up with this little example of confidence interval. So we've got a new printer that's been introduced on the market, and the manufacturers claim that an aligner on average is printed in 30 minutes or less. But you don't believe it. You don't think that's true. In fact, you think it's most likely far longer. So you conduct a null hypothesis test. Now your null hypothesis here would be that the manufacturer's claims are actually true and that it does print the aligner within 30 minutes max. And that is our null hypothesis. That is the one that we believe is not the true outcome. Our alternative hypothesis, on the other hand, would be that the mean outcome, or the mean time taken to print the aligner, is greater than 30 minutes. So you randomly sample some printer times for aligners and run the data through a hypothesis test, and your p-value turns out to be 0.001, which is much less than 0.05. So this means the results that you've observed are highly significant. So thinking back to our statistical significance and our p-test, in real terms there is a probability of 0.001 that you will mistakenly reject the manufacturer's claim that their print time is less than or equal to 30 minutes, since typically we are willing to reject the null hypothesis when this probability is less than 0.05. You conclude therefore that the manufacturer is wrong. Their printer times are in fact more than the 30 minutes on average. Now, thinking back to study design, and also bear in mind that there's going to be future lectures on critical appraisal, and as part of our critical appraisal, when we look at studies and see how they've been designed and if they've been designed correctly and appropriately, as part of this appraisal process of a study, we have about 10 questions we ask ourselves of the study. And one of these questions is, does the study test a stated hypothesis? Now remember, a hypothesis is a clear statement of what the investigators expect the study to find, and is central to any research, as it states the research question in a form that can be tested and refuted. A null hypothesis states that the findings of a study are no different to those that would have been expected to occur by chance. Statistical hypothesis testing involves calculating the probability of achieving the observed results if the null hypothesis were true. So we want to know, how likely is it that our null hypothesis is true? So you've done your test, but we have to be confident that this is actually applicable to the whole range of printers. So before you demand your money back, consider you could be wrong by having a sample with an unusually high number of slow printers just by chance. So how confident can you be in the result and that it's applicable to all the printers in that range? Now you'll recall from the previous lecture a type 2 or beta error. A type 2 error occurs when the null hypothesis is actually false but is shown to be true by our probability testing, and we get a false negative. Is where a test result indicates a high p-value that a condition failed when in actual fact it was successful, the one that got away. So this is a consequence of a small sample, and it increases the chance of your type 2 error. So again, if you're going to conduct a test on printer speeds, for example, conducting it on one printer would be open to criticism and the accusation of a type 2 error. Now, the confidence interval for our printer test, the average printer time was 35 minutes. With a 95% confidence interval of between 31 to 39 minutes. So that means that over 2 standard deviations, we have the possibility of getting either a print time of 31 minutes to 39 minutes. So although the printer speed was a little bit slow, we do know that on the higher end, we could go up to 40 minutes. On average, you're looking at 35 minutes, and the best possible result we can look at is 31, and they're all higher than the stated 30 minutes or less by the manufacturer. And we can say this quite confidently that at 95% of the time we're going to get a result somewhere within this range. And that's within 2 standard deviations. So you can see that it is a difference of 4 minutes, either 39 or 31 minutes. So we have a 4-minute variation there, and that will occur 95% of the time. Our range of values. Obviously you could get something print at 34 minutes, 33 minutes or 38 minutes. It won't be exactly 31 minutes or these 3 figures. It will be in the range, but we can be 95% confident that the result from the printer will be somewhere in that range. The lecture has covered confidence intervals and how they are necessary in determining whether results are actually clinically relevant and significant, and how they relate both to our p-values and also to our standard deviation.